So I'd like to thank the organizers for the invitation. So what I'm going to talk about today is a joint work. So it's based on two joint work, one with Dan Xie and Wenbin Yan, and another with Wenbin Yan and Qixian Zhao. So what we're trying to do is to try to propose some relationship between representations of affine vertex algebras and geometry of affine Springer fibers. So let me start by introducing some notation. So let's start with a simple complex Lie algebra. And I will fix a Borel subalgebra in Carton. And then for each simple Lie algebra, we have an affine Lie algebra, which is the central extension of the loop algebra. So here, this identity is a central element. Then the bracket is given by x tensor z to the power of m, y tensor z to the power of n is equal to your bracket on the Lie algebra times z m plus n plus m times delta m plus n0 of a certain times a certain pairing x and y on G, which is just the Killing form divided by twice of the Dirac-Coxeter number and times the identity element. Okay. Okay. And then here I have. So we will be interested in representation of this affine Lie algebra, and in particular, there is a very important module, which is if you fix a complex number k. And then you can consider a trivial module for the subalgebra which has positive loops. So GZ acts trivially, so x by 0. And then I ask the center acts by k. So acts by k. And so then it's a representation of this subalgebra, and I can induce it to the enveloping algebra of the entire affine Lie algebra. This is a particular G hat module of level k. Level means how the scalar by which the center element acts, and we'll denote by this by Vk of G. Okay. And it turns out this space has the structure of a vertex algebra. So I will not go very much in detail in vertex algebras, as you will see later that my talk is more concentrated on representations of affine G algebra. But nevertheless, I want to just say a few words to give you a sense of what structure this is. A vertex algebra is the data of a vector space V, a vacuum vector, which is just a vector in V, and a translation operator on V. And more importantly, there is a so-called state field correspondence which is a linear map from V to endomorphism of V. So where epsilon is a formal variable. So the idea is for each vector in V, you attach a series of linear operators on V. So sum of A n epsilon to the power of minus n minus 1. So such that for each vector in V, that this an of V is 0 when n is large enough. And it satisfies a list of axioms, which I will not write for you. Satisfying a list of axioms. Okay, and so in this case, for the maybe I'll just say for VKG, so on VKG, the vacuum is just the vector 1 tensor 1. And then the state field correspondence is determined by how you send. So you see, by PPW theorem, this has a basis formed by monomials of the form X tensor Z inverse. And so I just need to explain you how to. So Y of a vector, let's say A tensor Z inverse is given by sum of A tensor Zn epsilon minus n minus 1. Okay. So this is the structure of a vertex algebra here. So it's called universal affine vertex algebra. And this thing, first as a representation, it always have a unique simple quotient. So we'll denote LKG to be the unique simple quotient of VKG as a G hat module. And it inherits a vertex algebra structure. So it's and moreover, so for vertex algebra, as for algebra, you can talk about whether an algebra is simple or not. So this is a simple vertex algebra. Okay. So another thing. So how is this related to representation of affine algebras? So one can just check if you consider representation of VKG. So these are some vector space where you have, for each vector V, each element in V, you associate a field of endomorphism of that module N. This naturally, just tautologically, basically, equivalent to what is called smooth representations of G hat of a level K. Okay. So smooth representation just means it's a vector space such that so this means locally. So A times Z n x by 0 x on, yeah, okay. For any vector, this is 0 for n large enough. So it's the same condition as this one. And LKG is the quotient of VKG. So for any representation of LKG, you can pull it back, and so you can pull back a representation to obtain a module here, and this is a fully faithful embedding. So this is a full subcategory. Okay, and then we'll be interested in the subcategory. That I will not be interested in all the entire category of representations. Rather, I'll be interested in so-called the category O. So here, I have a subcategory which is called category O. So this consists of highest weight representations, or generated by highest weight representations. And so we can ask what are the what are the modules here, which are representations over LKG. So this category I will denote by CK. So CK by definition is intersection of OK with rep of LKG. Okay. All right.
So you wrote for us a formula for y of A then is inverse?
Yes. -2. I think those things you can deduce from these formulas by doing the bracket. Yeah. Okay. So this is the category I would be interested in, and whenever you have a representation category, the first question you want to ask is what are the irreducible objects in it, and how is it parametrized? So, so in this talk, we'll be interested in two kinds of questions. So, so problems we'll be interested. First is to classify irreducible objects in this category of CK. So this set I will be denoted by E-rep of CK. This is just the highest weight representations of LKG. And a second problem is to describe what is so-called the associative variety of this LKG. So by continue here, let me explain. So what is a associative variety of a vertex algebra? So for any vertex algebra, Yongchang-Zhu attached an associative and commutative algebra RV, which as a vector space is just defined as V quotient by the span of elements of the form A-. So A minus 2 is just the Fourier mode there with n equals to -2 for AB in V. And one can check on this space. So if you look at so an element, I write A bar as its image in here. The product is given by just you do A minus 1 applies to B and takes the bar. And one check, this defines a commutative algebra. And moreover, it is Poisson. So it has a Poisson bracket, which is given by taking A0 B bar. And so in particular, you can take the spectrum of this commutative algebra. So for our purpose, we will just be interested in a reduced structure. So I always consider the reduced scheme associated to this. And this, I'll call it XV. This is the associated variety of the vertex algebra V.
Is the subscript on A?
On A. This? Yeah. This is -1. So this is the coefficient here when you do the state field correspondence. Other questions? So, so this is an important invariance of a vertex algebra, and you would like to understand what it looks like for this LKG. So one thing you know, and it's not so hard to pin down, is if you take the universal vertex algebra, this associative variety is as a Poisson variety is isomorphic to G dual with its usual Poisson structure given by Kosten-Kihilov bracket. And so LKG is a quotient, and one can check by that definition the Zhu algebra, Zhu C2 algebra is also a quotient. So this is a closed subscheme inside here. So it's a Poisson subvariety. And moreover, there's some conformal structure on these vertex algebra, which basically says, so it's compatible with the dilation C star action here. So this is a conical Poisson variety. And this should be a conical Poisson subvariety. And the question is what is this? So, okay. So the answer of these two questions depends on the value of k. So for example, if so maybe some examples. So first of all, if your k plus the dual coauxiliary number is not negative, it's not a negative rational number, then in this case no, did I? Just a second, I think. Maybe I want not a rational positive number. Then this VKG is just simple. And so in this case, we know the answer for both questions. So the associative variety is G dual, and this is just all the highest weight representations. So this is easy. And second, if k is a positive integer, then this case is well studied. And so first of all, the irreducible representation of LKG is just all the integrable highest weight, all the integrable G hat representation, irreducible, of level k. And the associative variety in this case, what's the notation? LKG. In this case, it's just a point, 0. And so the answer is also known in this case. And then if you restrict yourself to the interval, let's say if we restrict us just to integers such that k is negative, but k plus h check is positive. So I do not consider a critical level, so I will exclude minus h check. So when it's between minus h check and -1, then this vertex algebra has not been well studied, and basically nothing is understood. Well, except some particular examples where people could compute by hand. Well, there are some results, but it's not so well understood in general. So this will be a case which is of our interest for this talk. But I want to start by discussing another case, which is called boundary admissible level. So this is the case where k plus h check has the form is a rational number of the form h check over u, where U is a positive integer and co-prime to H check. And in this case, the irreducible representation, irreducible highest weight representation has been classified by Katz and Wakimoto. And the starting point of our project is we give an interpretation of this, this set from the point of view of affine Springer fibers. So now I want to make the connection to affine Springer fibers. Okay, so from now on, I restrict myself to G simply laced case just to simplify this talk, because if G is not simply laced, I need to consider some twisted affine Springer fibers. And let me fix some notation. So I will take G check to be a connected and simply connected algebraic group, reductive algebraic group, such that the Lie algebra of G check is the Langlands dual of G. And then I fix Borel and maximal torus, so over C. So I fix Borel and maximal torus, which is corresponding to the data we fixed at the beginning. And so as we have seen several times, so we can consider the affine flag variety for this group. So let me just fix some notation. C of C, and then so I have G, the loop group GK, GO, and the Iwahari subgroup, which is sorry, G check everywhere, which is the pre-image of the Borel under the evaluation map. And so we'll consider the affine flag variety, which is G check K mod Iwahari. And when you have a element in the Lie algebra, well, usually we take for the fiber to have good properties, usually we take this to be a regular semi-simple topologically nilpotent element, although for the definition it's not necessary. So by the affine Springer fiber corresponds to this gamma is a closed end scheme inside affine flag varieties, consisting of the points, so Gi check such that a joint G inverse of gamma belongs to the Lie algebra of I check. Okay, so if we put this condition, this is a in scheme locally of finite type. And for our purpose, for the discussion about this boundary admissible level, I will consider a particular element, gamma, which I denote by gamma u. This is the element which you take the sum of a root vector for each simple root, for each finite simple root, and then plus f of the highest root, the negative, a root vector in the negative of highest root, times z to the power of u. Okay. If we're in GLN, this is a matrix of the form. So you have 1 on the upper diagonals, and you have z to the power of u here. Okay. So this is a so-called homogeneous elliptic element. And in this case, the corresponding affine Springer fiber actually is just a usual like finite type scheme. And moreover, this homogeneous condition just says it has a C star action on it. and as a fact that the fixed locus is just a union of finitely many points. So this is so this is it's a finite set. Okay. All right. Arrange my bullets. U is an arbitrary integer which is co-prime to h check. So I have U on both sides. K for the level k plus h with h check over U, and then on the for the gamma U also depends on U. And so the first theorem we prove is the following. So this is in the first paper. So for k plus h check equals to h check over U, with U as above. First, we show there's a natural and explicit bijection between irreducible representations of this admissible, in this category CK. So between this set and the fixed points in this affine Springer fiber. So produce some explicit bijection. Moreover, this bijection satisfies some nice property. So first of all, actually in this case, this is a semi-simple category, and so the characters of G-hat modules satisfy some modularity property. This was proved by Katz and Wakimoto. So in particular, if you consider the Grothendieck group of this category, it has a basis given by the characters of the irreducible representations. And the modularity property tells you that this space carries an action of SL2Z. So this action comes from work of Katz and Wakimoto. And now on the other side, I can consider the equivariant K-theory of this Springer fiber. And I specialize the parameter Q to be exponential of 2 pi I of h check over U. And a bit similar to the moral in Roman's talk this morning, actually. So this is the same as the K group of the cyclic fixed points here, but actually in this case it's the same as the K group of the fixed points by C star. But this is just a bunch of points, so this is just functions on this finite set. And the characteristic function form a basis. Therefore, this explicit bijection produced me an isomorphism of vector spaces. So this comes from this So I take the bijection comes from, the isomorphism comes from this bijection. And
You mean that you're sending irreducible to?
yeah, I'm sending the character of irreducible to the characteristic function on the corresponding point. There's a modification by sign, but that's roughly the map. And so for people who were here last week, we discussed affine haiku algebra action on homology of Springer fibers. So here you have an analog construction due to Vasseau, which is an action of Daha on this space, and it realizes a finite dimensional representation of Daha, and Cherenik constructed from this point of view an action of SL2Z on this space. So we show that this isomorphism intertwines these two SL2Z actions. Okay. And finally, so there is some compatibility, which I would just mention without going into detail. On vertex algebra, one can perform a so-called Drinfeld-Sokolov reduction. To obtain from representations of LK to obtain irreducible representations of W algebras, which depends on some nilpotent element F. On the geometric side, you have a kind of reduction from Springer fiber to Spatishtan fiber to Spatishtan varieties. So here you have a reduction to Spatishtan varieties. And under the bijection we are discussing, these two corresponds to each other. So modulo probably some conjecture on irreducible of W algebras, which I think Gerber Dillon has claimed he has approved, that this compatibility induces a bijection, a similar kind of bijection between irreducible of W algebras and C star fixed point in some Spatishtan, some sort of parabolic version of this Springer fiber. Okay, which again intertwines the SL2Z action.
What is this?
F is a nilpotent element. No, I need to nilpotent element which is regular in a Lévy. And this parabolic is the parabolic with the Lévy. Okay. Other questions? Reduction. The reduction is a functor from LK modules to WK modules. Yes, it kills some simples and it identifies some other set of simples. And so those which they kill are those doesn't belongs to the radical of the parabolic, and which identify are like identified under quotient by G with P. Okay, so this is the main result of the first paper. I think I want to say a few words about the motivation, like how we came up with this result. It actually comes from some physicist motivation. Like my other co-authors are physicists, are math physicists, and this is what they explained to me. So the idea is maybe like remark. So for any 4D n equals to 2 superconformal field theory, there is a work by a group of physicists and others. So to each such theory, they attach a vertex algebra. And for a theory like this, so for each theory there's a vertex algebra V. And each such theory has a so-called Higgs branch and a Coulomb branch. The Coulomb branch. And the Higgs branch is supposed to be given by the associative variety of this vertex algebra. And for a particular type of theory, which is called class S theory, or let's say generalized class S theory. So these are some theory coming from a 6D theory, but you compactify on the Riemann surface. So in particular, any such theory depends on the Riemann surface. And the Coulomb branch is by work of Gaiotto. Moore and Nitsky. The Coulomb branch is given by the moduli space of Higgs bundles on this Riemann surface C. Okay. And for what is relevant to us is this LKG for admissible level. This LKG appears as image of some class S theory. So I will just put TKG here. And its Coulomb branch is given by so it's a moduli space of Higgs bundles on P1, but with a regular singularity at 0, or maybe I should put more generally W algebras. And the type of regular singularity of 0 will be depend on the type of the nilpotent element. And so this is related to F dual actually. And then there's a irregular singularity at infinity, whose order of pole is related to the choice of this K. And then they have some prediction that irreducible of this vertex algebra should be corresponding to C-star fixed point in this Hitchin system. And this has a central fiber, which is, so it has a central fiber which is homomorph to the Springer fiber we have been considering. So I think a proof of this fact appeared in a paper by Roman and Brazeda Alvarez and Michael McBrain and Zhiwei Yun. So it's the kind of Hitchin moduli space considered in their paper. So this is why so our result is motivated by this picture. And this also motivates our further study because...
Can I ask a question?
Sure.
Maybe the answer is just mathematics, but how do the physicists know that they get specifically the simple quotient of the
I don't know. So I think for them it's... Good question. I think they're... So they don't know you get the simple quotient. They only know the simple quotient always embeds in their vertex algebra. So I think what I said for them is just tested in some examples and they observed this, but I don't think they claim it is true. And we'll see later that actually those comes from physics theory more generally should be some extension of this simple quotient. I cannot provide a good answer for this. Yeah. I think their argument for having the simple quotient is just that you have this gate group symmetry there, and so you should have a map from this vertex edge from LKG to the vertex algebra you're considering. But okay, and so this also motivates our study for this kind of levels because. So they have shown that for such levels, I will call them these non-admissible levels. So maybe second remark is that this LKG for K belongs to this interval also appears sometimes as an image of certain theory. So it's interesting to know when does a certain LKG appear as an image of a theory, but somehow physicist says their vertex algebra should always be quasi-Lees. So that's physicist's expectation. That this VT is always quasi-Lees. What does that mean? That means so this by definition. This associative variety, which is a Poisson variety, only have finitely many symplectic leaves. Okay. So if we're concerned about LKG, you can first ask for which K this LKG set is quasi-Lees. And it's very easy to see it's not true for all K because just for what I just erased, if K is not, K plus H check is not a positive rational number, then LKG is just entire VKG, and so its associative variety is G dual, and that has infinitely many symplectic leaves. So the question is, so this raises a question. So when for which K LKG is quasi-Lees. Okay. Okay, so we'll move to the non-admissible case in a second, but I first want to discuss more about this admissible case. So I told you how the irreducible objects look like, but we haven't discussed the associative variety in this case. The associative variety has been computed by Arakawa. So he has shown So Arakawa showed that for K plus H check equals to H check over U, the associative variety of LKG is given by the elements in G. Well, if we identify G and G dual such that a joint of x to the power of 2u is 0. So this is, in particular, this is contained in a nilpotent cone. And well, so this is a quasi-Lees situation. And now you ask yourself, how is there a way to see this associative variety from the affine Springer fiber point of view? Like is there a way to produce this from the Coulomb perspective? So we have some observation on this. So first of all, I will need to introduce some convention. So if I write Gehör gamma so we have the affine Grassmannian is G check K over G check O. And then Gehör gamma is all the elements in this coset such that adjoint G inverse of gamma belongs to G check of O. And in particular, I have a map from here to the nilpotent orbits. So N underline means the set of nilpotent orbits in well, you can write it as a stack, but I only care about the set, the structure of the set. So simply just, you have an element here, and then you know after conjugating it by G, the conjugate by such an element of gamma is in G hat of O. So you can specialize Z equals to 0 for such an element. So there's an ambiguity of cosets which provides an ambiguity of the G-check action here. So at the end, what you get is an orbit. It's a nilpotent orbit. So it's the G-check. So it's G-check applied to such an element. Okay? Okay, and the so-called reduction type of gamma are all the nilpotent orbits which appears in the image of this map. Maybe I should put a check here. So reduction type of gamma is the orbits in the image of this evaluation map, and in which you can take the subset of minimal elements in this set. So with respect to the partial order given by the inclusion of the closure. So minimal elements in RT gamma, which may not be unique in general. But for this particular element we have been considering, so RT min of gamma u it just consists of a unique orbit, which I'll denote by O gamma u. Check. And the observation is at least in type A, this orbit is related to, okay, so maybe I should first say that this is the closure of a certain orbit. Maybe I just write it as OK bar. So the observation is that okay, there's a so-called Babbage-Wogan Lustig-Spaltation duality map. It's a 3 different paper defining it in 3 different ways. From the nilpotent orbits in the dual Lie algebra to the nilpotent orbit of G. So in type A, this is just your nilpotent orbits parametrized by partition. You just take the transpose of the partition. But in general, this map is much more complicated, and in particular, it's not surjective, neither injective. But this is a very important map in representation theory, and the observation is that D of O gamma U dual is equal to that orbit over there. In other words, the closure of this is the associative variety of LKG. Okay. So, well, this doesn't work. This works in many cases, but doesn't work in all cases. And I think now we come to some understanding of how to formulate this more properly for rational level to really have a statement like this. But I will not talk about that today. Right. So the moral of what I'm describing here is that there should be some relationship between this RT-min construction and the dual of it and to the associative variety of this LKG. So, so now I want to move to the non-admissible case. This is studied in the second paper joint with Wenbin Yan and Qixian Zhou. Yeah, yeah. So now, from now on, I assume k plus h check is equal to m. And it is in the region I'm interested in, meaning m is an integer among 1 and h check. So we want to study this case, and more particularly, I want a statement of the similar kind. Like, so the problem is so you want to find the gamma, so you first want to find some orbit, some nilpotent orbit, which allows you to describe the associative variety. And also, you want to find an analog of gamma, which is a regular semisimple topological nilpotent element, such that the analog statement, you have some correspondence between the Springer fiber of this element and an irreducible representation of CK. And more precisely, actually, we want some relation between the Springer representation corresponding to this element to irreducible representation of CK. And so you need the recipe to find this. And the recipe we provide is the following. So you, maybe I just, let me see, shall I start with the definition or? Yeah, I just start with the results. So the main results we obtained in this paper are the following. So as was mentioned in Charlotte's talk this morning, so for loop group, there is a similar bijection between conjugacy classes of vowel group. So this is conjugacy class of vowel group, and conjugacy classes of maximal torus in the loop group. And so, so the map RT-min I described to you is really a map from this conjugacy classes of vowel group to the conjugacy classes of nilpotent orbits. I will work on the dual side here. So this map, more precisely, it is given by taking the intersection of all the RT-min gamma such that the centralizer of gamma has type a given conjugacy class W. So RT-min of this W And you take intersection over some gamma with minimal valuation. This is called shallow elements by Yun. And he proved that there is a unique conjugacy, unique nilpotent orbit in this intersection, and therefore you have a well-defined map like this. And it coincides with the map defined by Lustig in some other ways. And it has a section which is called Kashtan-Lustig map. This Kashtan-Lustig map, I change the color. It is given by, if you have a nilpotent orbit, then you take some gamma, some generic Luft of E, well, in the sense of paper of Kashtan-Lustig, and then you take W to be the type. So this is sent to W is the type of the centralizer. Okay, and for our purpose, we want to attach some integer to nilpotent orbits. So we first consider a map from this conjugacy of vowel groups to integers, turn 1 and H check. It's very simple. It's just you have a conjugacy class, and then Wx on the Lie algebra H, and just by the usual reflection representation, and its eigenvalue is some roots of unity. You just take the maximal order of roots of unity in eigenvalues of W on H. Okay. And what we show is that this map factorized through this quotient, and so it gives you a map from the nilpotent orbit to here. So this map, so this factorized such that this map, commute. Okay. And actually, I'll not describe for you, but this map is explicit. It can be described explicitly on the orbit. And in particular, you can compute it for all the nilpotent orbits. And I think we did that. Okay, maybe down the first border. Just do this. And then we prove that for this map from the nilpotent orbits to Z, it has a nice property that, so that was the first. And second, we prove that for any n in this interval, the pre-image of this map, which I denoted CLN, of the interval 1 and n, contains a unique maximal orbit. Unique maximal orbit, which I denoted by O check of n. You can show that this map increases with orbit. Like when your orbit is getting bigger, and then the value of it under this map is getting bigger. And moreover, actually, so this orbit can be computed explicitly, and turns out this is given by x in G, such that just a joint action of x to the power of 2m is equal to 0. Okay. So basically, this will be the kind of the orbit we want to attach to this vertex algebra, and we proved something more about this orbit which will be useful for a picture I will explain at the end. So you remember we started with this vacuum module whose highest weight was k lambda 0. And if you do the row translate of that weight, so k lambda 0 is 0 fundamental weight, plus row check, then this is m lambda 0 plus rho, just by definition. And when m is in this interval, this weight is not dominant for the affine weight. And so I will take psi m to be the unique dominant translate in sense of affine weight translate of this weight under the affine vowel group action. And for m in this interval, this is a singular weight, so in particular has a non-trivial stabilizer. So Wm is defined as the stabilizer of psi m in W affine. But now this is a finite reflection group, so it has a longest element, which I denote by small Wm. So this is longest element. And then we show that this orbit is the one corresponds to the two-sided cell of this element under Lustig's bijection. So under the bijection between nilpotent orbits and two-sided cells, in W affine. So this is Lustig. This O check M matches with the two-sided cell corresponds to this element Wm. Okay, now I can say the one of the main results is also we provide a conjecture for the associative variety. For the associative variety of LKG, the conjecture is as follows. So I fix, again, m equals to k plus h check. And then I had this orbit defined for you. And so what we do, you first write this orbit as a saturation from a levy of G check of a distinguished orbit in levy. So OL check distinguished orbit in L check. So this is by Bala-Carter classification. You can always do this. And now the conjecture is the associated variety for LKG is given by the so-called the sheet attached to this levy, the Langlands dual of this levy, which is I denote by L, and the Babbage-Vogel-Lustig dual of this orbit. So what this notation, take the closure. And what this notation means, where, in other words, so this by definition is you just consider the map from G cross P of the Lie algebra with the action to G. And in the Lie algebra of P, you will put this orbit, the dual of OL check, and you will put the center of L, and then you will put the radical of P. And just take so this is the action map multiplication. And then just take the image of this. This is the definition of S. Okay. So this is interesting because it provides a uniform, at least conjecturally, a uniform description of this associative variety which didn't exist before. And we show that this is true in all the cases where this XLKG has been computed. So actually, for this conjecture, everything on the right-hand side of the equation is explicit. You give me a G, give me an M, and I can tell you what does the right-hand side look like. And the problem is this is not well understood, but some people computed this or provide some description in some particular case, and in all those cases, this conjecture works. And moreover, if it is true, it also gives us a criterion about when does LKG is quasi-Lie. So is this correct? Yeah, so this was my problem. I leave it here. So it's a corollary is that if this conjecture is true, then let's say conjecture implies that LKG is quasi-Lie if and only if this orbit O check M is distinguished itself. Okay. If it's not distinguished, then the center of the Levy will consider some torus part, and that could never be. So you wouldn't get any finiteness condition. So actually, if this description is correct, then the associative variety has finitely many symplectic leaf. This is equivalent to say this is contained in the nilpotent cone, and which is equivalent to this. Okay. So this gives you some. So this condition can be explicitly checked for each m, and that's okay. All right. So this is the question about the associative variety, and then I just want to give some, explain some speculations or expectations of for the classification of irreducible representations. So this is some of this is being written down, but it hasn't appeared online yet. So let's see what we have done. We started from some m in this interval, and then we attached some orbit O check of m. Okay. Maybe in this discussion, I will restrict myself to the distinguished case. So assume this is distinguished. I mean, just. It should work more generally, but it's just safer. At least for this case, we understand better what's happening. And then, as I explained, this corresponds to, under Lustig, this corresponds to this two-sided cell. And then here we have the duality map, which sends this to dual of O check of M. And the associative variety conjecture tells us its closure is the associative variety of LKG. Well, conjecturally, this is the conjecture on associative variety tells us is related in this way. And now you can consider the So now I consider the K0 of highest weight representation here. That means I consider the K0 of this category CK I explained here, but actually I need to take the principal block for the discussion here. So this is all the LKG module in the principal block. And the conjecture is that so first we know it carries some affine vowel group action and by twisting functors, and this should isomorphic to the left cell module for the affine Haiku algebra. The left cell module corresponds to this element Wm, where I need to take the dual form in the Haiku algebra and specialize at q equals to 1. So this is a conjecture. And then, so in particular, this is related. And then on the Haiku algebra, you have some sort of duality between this left cell module and the right cell module for the dual form. Q equals to 1. And this is supposed to surjects onto the, okay, I take gamma to be a generic lift of an element in here, and then this again, this is less conjecture than that, but it's supposed to be maps onto the H top of this affine Springer fiber invariant by some component group, and yeah, so this provides you some relationship between the affine Springer theory of this fiber and this so irreducible representation from a basis here. So you don't have an isomorphism in general, but you get some correspondence with the Springer representation. I have 5 minutes, I think. Yes. So I want to just explain why we conjecture it this way. This follows from some analogy from finite type, which is a classical story. So I've been talking about this duality map through my talk, but I didn't give you a definition. So maybe now is the moment. So analogy in finite case is, so there we need to go back to the definition of this duality map from n check to n by following Babbage-Vaughan's definition. So their definition is the following. You start from some nilpotent orbit here and say O check here, and then you take an element E. You complete it into an SL2 triple. So E, H, and F. And then the semi-simple element is an element in the carton of H check. And in particular, this identified with the dual of the carton here. So you can, so this H, you identify it as an element, let's say lambda here. And so such an element determines a central character for G. And so it turns out there's a unique maximal primitive ideal in UG with central character given by this lambda. Okay, and then there's a classical theorem due to several people, Borel, Brylensky, Joseph, and others, which shows that if you take UG quotient by this primitive ideal, take the associative variety of this, just taking the associate graded and in the spectrum, this is the closure of some nilpotent orbit. And this O lambda is the image of O under this duality map. So send to O lambda. Okay. And now assume that E is even. So in particular, all distinguished elements are even. But so assume E is even, then, lambda is half of H. So if lambda is even, then this is an integral weight. So if E is even, then lambda is integral weight. And let's assume it's dominant. So we have choice on lambda. And then, so we can just play the same game. I take W lambda to be the longest element in the stabilizer of this W lambda. Then I have a similar diagram, which in this case are all theorems. So I start from E even in an orbit O check. And then this duality map sends it to O lambda, which is the associative variety of UG quotient by this primitive ideal J lambda. And in particular, I can consider modules of this quotient inside the category O of G, and in the principal block. I take the K0 of this, and so this O corresponds to the two-sided cell for this element W lambda, and then in this case it's a theorem that this is, I think, of Babbage-Wogan, that this is isomorphic to the cell module in the finite Hecke algebra of the left cell for this W lambda. Q equals to 1, and then here you have the dual form. Sorry. Which maps onto the Springer representation correspond to this element. So this is a quotient as a W representation. Okay. So what we propose is an analog picture in the affine case, which helps to understand the representation for the affine vertex algebra. Okay, I stop here. Thank you.
Thank you very much. Other questions?
Well, I mean, there's a general question. So these vertex algebras are related to chiral algebras. Is there like a description of the associated variety in this language?
No, I don't know. I actually have a question for the audience. So I was just wondering, this vertex algebra exactly has a chiral structure, and then so we're trying to relate it to some Springer fibers, and are there some sort of chiral structure on the Springer fiber side? So yeah.
And well, maybe more like minor question. So it's like you were considering this two-sided cell corresponding to the longest element in some stabilizer.
Yes.
But I mean, if it's a Coxeter subgroup,
yes,
generated by simple reflection, that I guess this is just the Richardson kind of element was parabolic. But in this more, your construction is more general.
Yes.
In these more general cases, is there more like explicit descriptions
of this two-sided cell?
Or this linear-potent element along these lines?
So, wait, I probably need to answer this question later. So you say when this is generated by Coxeter element, it's
by simple reflection.
By simple, it's the one corresponding to Lustig is a Richardson orbit, or
yeah, I think so.
Yeah.
Okay.
You mean okay, yeah. Like for our WM, then this is explicit, but more general than this, I don't know.
Are there any more questions?
There's a question in the.
I'm not certain if this is like a very intelligent question, but how does your discussion of the irreducible representations of the W algebra fit with the affine Scriabin theorem, at least in the principal case? Like, does your
Fit with
affine Scriabin theorem that relates the representations of the W algebra to the certain invariants of the G modules? Is there a way to nicely describe which G modules you see from this?
I don't know.
Right. So you had this bijection between these irreducible representations at the boundary admissible levels and these. So is there any hope to get this as some kind of equivalence of categories or something between the?
There are some guess about that, but in this case, it's a semi-simple category, and then the idea is to use some metaplectic cover. So maybe I should explain. So all this of kind of correspondence should be related to some causal duality, where the representation. So we have this basic having covariant causal duality, which relates category O for G hat and category O for the Langlands duo of G hat. Actually, for our picture, if it's not simply laced case, it's also the Langlands duo of G hat which appears. And this is a sub category on one side, and on the duo it should be related to a quotient category. And then if you take for integer level, that's exactly what we expect to happen, and that quotient should be related to this Springer fiber. But for the rational level, one need to take some sort of metaplectic covers on that side to match up the bijection. But
All right, any more questions? Okay, so if there are no more questions, we can thank Peng again.